create this within a digital, within an artificially created universe. And he's working completely. The other guys are working in hexadecimal. They have a shorthand, but he's still working totally in blank, raw binary. And is trying to learn about how life, he's interested in genetic code, he's a biologist, but he sees the computer as a way to model what might have happened at the beginning of life on Earth. So what he did was very profound. It's still not been caught up with by a lot of modern sort of computational biologists. And he ran these things, he printed them out on IBM cards and contact printers, so we have these fossil inference of what he was doing. He built a cyclical universe because he didn't have enough memory to make it very big, but it ran in circles, like an ant crawling around inside a wine bottle. And that was beautiful stuff. Then he realized we had to have diversity, so he does 3 different universes and allows the organisms to go back and forth. But they're just numbers, they're not going to do anything. So he saw that right away. We had to actually, like, software, doesn't have any real effect until it goes out and does things, which is what we do when we create an application. You find a way to apply these numbers to something in the real world. So when I was there digging around for evidence of this in the basement of this place that sort of denied the existence of any of this had ever happened, we turned up a box that had a whole set of punch cards and the source code written for one of his universes. And in that node it says to Mr. Garchad, there must be something about this code that you haven't explained yet. And it's still true. We have not explained how these sort of one-dimensional self-replicating codes can become sort of three-dimensional living things in the real world. That's a question that Neumann was trying to answer. Is a question that most of biology is still trying to answer. Neumann died tragically when he was 4 years younger than I am now, and with cancer. So he was thinking about the future, but he never got to see that future. But left this bit of wisdom to you programmers. It's easier to write a new code than to understand an old one. And that's I think the reason we have such a monumental complex codes, because it's easier to write something new on top of it and understand what was done earlier. So the person who sort of remained the legacy, who knew what Neumann was thinking about when Neumann died, was Julian Bigelow, who was unfortunately silenced. And he gave us sort of our last sort of deathbed words of what Neumann was really thinking of. That we really got stuck. It's absolutely amazing. We live in this world. I mean, Von Neumann and Bigelow would be astonished when we came back 60 years later and found we were doing everything the same way they did. They just did this to solve the hydrogen bomb. They didn't expect us to do this for 60 years. I mean, it was just an approximation of what could be done. So the fact that we write these highly recursive software that recall things, it's just because we're trying to feed these machines can do 1 billion instructions per second. We can't write 1 billion instructions per second. So we've been really confined by this sort of having to write recursive programming. The other thing that bugged the hell out of Von Neumann and Bigelow was that we were stuck. We had to address it. The way the computers were built, and in the way you're doing it in time, you have to refer the instructions by an address. So you're limited by just one address at a time. But the computer is capable of doing infinitely more than that. We're just not using it, and we're still not there. And the fact that we got to billions of cycles per second means that we can still sort of tolerate this really bad. It's like this isn't gas that stayed 19 cents a gallon while we're still driving things with big inefficient carburetors. We don't need to. And then the whole question of why do we do things in this serial time way? There's also other ways to do computation. We're just not looking at that. So that's all I'm going to say about that. But Von Neumann left a lot of stuff unfinished that's worth looking at. What's interesting is that these are at this computer with their 5 kilometers. They worked on 5 different problems. And I put them on a time scale. They worked on nuclear explosions, which are over in 10 to the minus 8 seconds, all the way up to through shock waves, meteorology, which happens sort of in a matter of hours and days, biological evolution over years and thousands of years, all the way up to the evolution of the solar system over billions of years. So there's 5 different problems that were similar mathematically with different scales of time. And if you look at where we are, it's uncanny. I don't understand why this is, but as human beings, sort of the range we have from the blink of an eye, so the fastest thing we can perceive to life if you live 90 years and remember your whole life. In the middle of that is 8 hours. It's exactly in the middle of this range that computers have been expanding. They're expanding our view of time. And I think that's something that's going to continue to expand. And that's part of the boundary that we're pushing. Now, I'm not going to explain that. I'm just going to say that's a puzzle. Why are we right in the middle of this scale of time? When Ivan dies, 1957, they spend $15 for daffodils for his grave. So the machine that gets turned over to the university, Bigelow gets called back to run it. They finally shut it down. So midnight, July 15th, 1958, Julian Bigelow, he pulled the plug. The thing is running great. He's working on real problems, stellar evolution, physics, and so on. The university pulls the plug. And that's the end. So off 12 midnight, and he knows there's going to be no more entries in the log. So Ulam, Stan Rice says about them, he died so prematurely, seeing the promised land that hardly entering it. So this whole world was about to blossom, and you get to see it. It was the world that Leibniz, or the Old Testament prophets, which was essentially that God has made everything from ones and zeros. The entire world is a digital universe, and that's what. So I promised you a little bit about what's next. So I'm going to give you my 4, so you can remember them with 4 predictions. We got marketing lines here to keep track of predictions. What are the big things that are inevitably going to happen next? Okay, we are going to finally get to 3-dimensional computation. We're there already, we just don't recognize it. So, Turing's model of computation is one-dimensional paper tape. And what Von Neumann did, which was so profound, that's why we're here. He made that 2-dimensional. He did the 2-axis address matrix. So you could take a 5-bit on one axis, so 10 bits gave you an address that had a word of 40 bits. So you put in 10 bits, you get 40 bits back. That's like winning in Las Vegas. You're guaranteed to win. That's why this whole world of computation exploded and continues to explode. But it was still 2-dimensional. And the internet, when we developed the internet, which is now 30 years ago, it became 3-dimensional. You have a 3rd dimension to that address matrix, but we still are only looking at it through the Von Neumann 2-dimensional model. It's observed that we have not really developed a 3-dimensional model of forms of computation that are possible given the hardware. It's not that we have to invent the hardware to do it. The hardware already exists. We just have to get ahead of our models. And we don't have that 3-dimensional model. And then the other thing, which Von Neumann and Bigelow both were complete, 60 years ago, they told us this was going to happen. That physical accuracy, where you have to specify the exact bit where your word is. One bit is wrong, your whole thing crashes. Template-based accuracy, where you address by the contents of your memory, is infinite. That's the way biology does it. We don't say we don't know where that next molecule is going to be. We just know what template it's going to match, and that's why biology is so robust. And we now, and that's what Google is doing. Google is building a template-based map of the entire internet, and that's why they're worth a lot more than any of us are. And they have discovered this, but it's not part of our model of computation. The companies that develop code that works on template-based things, I'm going to go out and take this object that matches this template and do this with it, the same as we now have the instruction model with a strict address. That's the future of software, because it's robust. And it doesn't matter where the stuff is. You just take the next copy that comes along. The other one, that Von Neumann also wrote an entire book about, which is sort of forgotten, is pulse frequency coding, which is, he was interested in the question, how does the brain do computation? It doesn't digitally code. There's no code in the brain where you can decipher the meaning. It's pulse frequency code. This is the frequency at which neurons connect to other neurons. And that also is robust. It's 693 connections per second, or 741. It shifts the meaning, but it doesn't bring everything to a halt the way we do in digital computation. So that's a very key thing, and that's how Facebook and all these other huge computational processes are starting to use that. That's what Google is doing. It's counting the pulse frequency of connections between nodes. So that the final one that sort of draws all this together is we are going back, and nobody will talk about it. It's like a dirty word. We're going back to analog computing. where supposedly this is the digital revolution. It's the analog revolution. If you look at all the companies that are hugely successful, Facebook, Google, all LinkedIn, any of those things, they are doing analog computing. The code, the computation being done by the overall architecture is far more complex than the digital code which powers it underneath. And it's a very profound idea. I think that's the I'm going to end there, but that's the future. And it's not that digital is over. We're going to always have digital, but this is the new layer on top that's going to be the future success. Thank you.